I always find it helpful to remember the key steps in a test of significance to help the progress of working through these types of problems. In the previous video, we looked at a problem and we determined the null and alternative hypothesis. But let's return back to the general plans for a test of significance and how to kind of go about it. But our book uses a 4-step process for looking into testing, looking into significance testing. First of all, what's the practical question that requires a statistical test? Next is identifying parameters, stating the null and alternative hypotheses, and choosing the type of test that fits your situation. So far we've done this part. We've read through the question. We know why we are trying to do a test of significance here. It's because we have a particular statement about the mean of a population, and then we've gathered our own data, and we want to know if there is a difference between them. We've chosen the proper alternative hypothesis to be two-tailed because we don't have any assumptions about the 72 executives at our company and how they reflect about the company as a whole, about whether their blood pressure is lower or higher than the average. So, all those kind of go into understanding the situation at hand. Now it's actually the math. How do we solve it? How do we go through the math? So it's sort of like understanding the problem. That's the hardest part, in my opinion. And then running through the math is just a matter of calculating the p-value in the test statistic. So checking the conditions just means, okay, we want to make sure that this that it satisfies the conditions for the test. And we're going to learn more different types of significance tests for different situations as the semester progresses, like how to use them for proportions, how to use them when you don't know a standard deviation, and sort of look into some other alternative types of tests. But it's essentially trying to determine what test are we using. For now, we only know how to use the normal distribution in table A. So that's what we're going to do for now. Step 2, it says to calculate the test statistic. And step 3 is to find the p-value. So really, I think about this. This is the main part of the calculation. Is first, what's the test statistic? And this is very similar to with a confidence interval. Right? Like with the confidence interval, we have a formula for determining, okay, what is our, sorry, I'm trying to find the formula that we worked on in the last couple videos. We have a formula for determining this confidence interval. Now, the test statistic is a similar formula, which tells us it's going to give us some particular value. And to revisit that formula, let me find it in the slides, it is right here. It says that our test statistic value is z is equal to x bar minus mu naught divided by sigma divided by the square root of n. So let's go ahead and copy that down in our notes for the example as we try to find the test statistic and use a z-table. So notice it says z-score. Now technically a test statistic is not actually a z-score, but it's the same structure, and this is kind of how I like to remember it, because it's like x bar minus mu naught divided by sigma over the square root of n. But remember, a z-score is x minus mu divided by sigma. You take what is my score, subtract it from the mean, and divide it by the standard deviation, and that will give us a sense of where is it on the z-axis? How many standard deviations away is it from the mean? And at the end of the day, really, this is exactly the same thing. I'm trying to figure out how far is my mean value away from the assumed mu naught. And also, if you're like, well, what the heck is mu naught? Mu naught is just always equal to the null hypothesis mu claim value, which was that the average value, the stated value for mean systolic blood pressure was 130. And h sub 0 is always equal to mu minus mu sub 0. That's why they call it mu sub 0, because it's from your claim, it's from your null hypothesis. And then we take the difference of those. It's sort of like, well, like if we're putting our numbers into it, we calculated a sample from 72 executives that their mean systolic blood pressure came out to be 128.07. And that's different from the claim, right? And that's kind of like what a z-score does, is how far away is our data, this data point, from the actual average. And then dividing it by the standard deviation tells us, how many standard deviations is away. And remember, so the key thing about a sample is it follows the logic of sampling distributions from chapter 15. And remember that the standard deviation for a sampling distribution is based on the sample size. That's why we have the division by the square root of n here. but we take the standard deviation of the population and divide it by our sample size, because the larger our sample, the less variation we will have from the actual mean. And so in this particular case, the standard deviation of the systolic blood pressure from the actual population was 15. And then dividing by the square root of our sample size, which is 72, this will give us our test statistic for the significance test. And basically, it's much like a z-score, and we interpret that value exactly like we interpret a z-score. Because from there, we can then look it up in Table A to figure out what's the related cumulative probabilities like we did in Chapter 3. But before we do that, let's go ahead and calculate what this gets us. So 120, let me put the numerator in parentheses, 128.07 minus 130. Then I'm dividing by the standard deviation of the sample distribution, which is 15 divided by the square root of 72. And what this functions as is very much like a z-score. I get a value of approximately negative 1.09. And this, again, we would call this our test statistic for the significance test. And then we find a p-value from there using Table A. Or again, you can use various different resources to figure out what's the associated p-value from this. But let's go ahead and just go to ztable.com to figure out our probability for this particular z-score. So going now to the z-table, negative 1.09 would be all the way over here, and we get 0.1379. So let's copy that down. And again, kind of how I'm visualizing this is I have a normal distribution, I have an actual mean of my population, and then I have the value of my sample, which is about 1 standard deviation to the left. Oops, sorry, let me focus on what I'm drawing. And this is x bar, my obtained sample mean. And basically, because I know the behavior of the actual distribution, I can figure out what's the likelihood that I get a sample which is that bad. That's always what the p-value associated with the test statistic is. So our p-value associated with the test statistic is going to be 0.1379. Let me just double check. I think I remember what we got from negative 1.09. Yes. And this corresponds to the probability of this occurring. And so remember, small p-values are good. They mean strong significance. That means that, and high p-values are bad. So let's kind of revisit that in just a second. But one other thing that we don't want to forget about a two-tailed test is that technically we want to check the likelihood that our actual sample value would be either that bad or that good. So what this is saying is there's about a 13 to 14% chance that even if the actual mean was 130 for systolic blood pressure of men in that age group, that we would come up with a randomized sample of 128. As I said at the beginning, right, this is not that different. It's not, it doesn't seem like very strong evidence, but basically you have to factor in the sample size, you have to factor in the standard deviation to make sure that, because sometimes 128 could be wildly different depending on the usual distributions. But kind of the general sense about what blood pressures are, if you know anything about it, is there is variation among people. It's not, it's not uncommon for there to be pretty strong differences in people's blood pressure. But basically our alternative hypothesis was just, well, what's the chance that the mean is different from 130? So we don't want to just check the probability that it's less than the test statistic value. We also want to think about, well, what if it was also greater than? What if it was, because again, this is why we call it a two-tailed test. And essentially, the only thing you need to remember is that you want to double the probability that we get after all is said and done. Because essentially, this p-value, if putting it back into the proper statistical notation, we'd say probability that our test statistic is less than the value of z, which we come up with as the value from the table. And that would be if it was a left-tailed test. But if it's a two-tailed test, you want to double that value for your final probability, because again, the normal distribution is always symmetric, and the chance that our the chance that, for example, we could have gotten a sample like 132 as the mean value of our the men of that blood pressure. And essentially, we just want to know how extreme is this value. This one happens to be less, but we don't want to assume that we're always going to get something less. So we want to include the probability of that we would get something greater as well. So essentially, if we double this value twice that probability, we come up with 2 times 0.1379. And the p-value for our test specifically would be twice that. And we would get a value of 0.2758. And this is kind of like the final answer we're looking for in terms of making the final conclusion. And I'll talk more about the conclusion in the next video.